The last couple of classes we have been discussing adaptation using the least mean square algorithm. So the vector is updated using the gradient and the error. So x is the gradient of the equalizer output with respect to the coefficients, and E is the error of the equalizer output compared to the ideal values. So like I said yesterday, you don't do this updating in every data cycle, every cycle of the clock, because that will be too expensive in terms of power dissipation. So typically what happens is, if you have a high speed communication system, you have the receiver will have the equalizer followed by the decision block, and usually it also has a demultiplexer. Okay, let's say 1 to L DMUX. Now this is done usually because this is followed by some digital processor which works at a much lower data rate. So this is a high speed link. You can have a small part of the circuit working at the highest speed. Okay, but usually most of the circuit works at a much lower data rate, and it can, in this case, it can process an aggregate data rate of, let's say, 1 gigabits per second. But it's not necessary that the whole digital circuit be operating at 1 gigahertz. You can have 16 of them, 16 parallel sections which are operating at 62 megahertz and so on. So that's usually how it operates. Even when you say 1 gigahertz processor, very little of it actually operates at 1 gigahertz. A lot of the surrounding stuff operates at a lower speed. Okay. So because you have this, typically have this demultiplexer, you can also demultiplex the error and the gradient. That is simply, demultiplexing means that you just omit so many samples, right? You take one out of L samples or something. I mean, as far as adaptation is concerned, for processing the data you need all of the branches, but you do this updating, let's say once in L cycles. So if the entire equalizer is implemented digitally, it's quite easy. You just simply wait for L cycles and do the update and then wait for another L cycles and so on. If it's in analog, then you will have to compute the error and demultiplex that, and you also have to take the gradients and demultiplex that. So this may not be a full-fledged demultiplexer, right? Because you don't need every part of the data. You can omit some of the branches. Okay. So you demultiplex it and you run the LMS algorithm out of the demultiplex stream. Okay. The inputs to the LMS come from the demultiplex stream. So that is one. And if you are doing sin LMS, then this is the update in each coefficient will be minus mu sin of E sin of x of n minus k. So this is the coefficient for Ck. So instead of this, you do this, you update only one. So the increment in coefficient is mu, so, or rather minus mu, when this crosses a certain number, let's say m, that is simply averaging by m. Okay. You let this accumulate to a value m. So if this is alternating, which means that it is near the minimum of the error versus coefficient curve, then it doesn't do anything. Okay. Because the accumulator will increase and decrease and increase and decrease in alternate cycles. But if the coefficient really needs to be updated, this will be constantly 1 or constantly minus 1. So there will be a downward trend or upward trend in the accumulated value. Okay. So instead of just using sin E times sin this, you use this so that this is just to smooth out the variations in the coefficients. Okay. This is nothing but averaging the sin quantity. Any questions on this? So now we can go to more practical issues of how to realize these things. So I am assuming that right now this equation itself can be implemented as a digital circuit. You need a multiplier here, and in case of sin LMS, you need a bunch of XOR gates. You don't need a full-fledged multiplier. And you need an addition. You need an accumulator to increment or decrement the coefficients. Okay. So the block diagram will look like this. This is the decision block, and let's say all the delayed quantities are also available here. Okay. This is x of n minus k. If it's an nth order filter, you will have n such delayed variables which you need to take into the LMS block. And you realize the LMS equations in this. So this will give you, let's say this is an nth order filter, this will give you n coefficients. Okay. And this equation itself can be implemented by, let's say we have a sine LMS. The coefficient Ck can be held in a register. Okay. The register has whatever width, whatever number of bits you need for the setting the coefficient, and you feed that to an adder. Okay. What is the input to this? So sine of E, sine of x of n minus k. Okay. So it increments by 1 every time, and it's assumed that this scaling factor mu is implemented in whatever circuit is realizing the coefficient. So for instance, if you had made a differential pair, and let's say we implement the variable coefficient by splitting the tail current transistor M0, okay, and let's say we split it into 8 parts. Then if we call the full scale as 1, then the value of mu is 1/8. Okay, so each time it increments by 1/8 of the full scale value. Okay. So this whatever is stored here is multiplied by the increment that the actual circuit implements. Is it okay? No, so the mu is in this particular case implicit in how many pieces you turn this into. Okay. So you are asking where mu is implemented, right? Yeah, it is. So like I said, let's say when all of the transistors are on in the tail current source. So we divide the tail current source into, let's say, 8 parts, and yeah. So actually you can think of this as implementing, maybe I should have changed the notation. So I divide everything by mu. Okay. So let's say I have this. So whatever is in this register is really Ck by mu. Okay. That's all. So the number that is stored in the register is Ck by mu. And mu is a scaling factor that is in the implementation of the variable current source. Huh? This one? This one? No, this is just an adder. So are you familiar with accumulators? So digital accumulator is, you have a register, and this is, I think, the usual symbol for it. So this doesn't mean 1 bit. This can have as many bits as the register has. Okay. And to make an accumulator, you add the previously stored value to the current input to get the next value. Okay. So this is just an accumulator. This is implementing equations of the form y of n plus 1 is y of n plus x of n. Okay. Any other questions? So this LMS engine will be a bunch of accumulators like this. Okay. And if you implement averaging, it may be a little more complicated in that you need another accumulator to compute the average of this. Alright. So there are various ways of implementing it. You have the equations, and there are many digital implementations which will give you the same, which will realize the same system. Okay. So we get n coefficients, and these n coefficients are what control the equalizer. So these are the coefficients from the LMS block that drive the equalizer. Now, as I mentioned earlier, this updating first of all doesn't have to be done in every cycle of the data, and you can implement averaging also. Okay. So, what are all the things we need? I mean, right now we won't concentrate too much on how we implement this equation. That's a kind of a trivial digital circuit, some accumulator and so on. So, that we assume we can do. Okay. Especially because it can be done at low speeds. Right. Once we have the digital inputs, we should be able to realize an equation of this form. At least for sine it's very clear. It's just an accumulator. If you have the full LMS, you will need multipliers and so on. If E and X are represented to accuracy more than 1 bit, then you will need proper multiplication and accumulation. Otherwise, it's simply a 1 bit input which tells you whether to increment or decrement the counter. Okay. So, this part is simple. We have to be able to implement the error, and we have to be able to take the gradients out. Okay. So, firstly, how do we measure the error? How do we implement the decision block? Huh? What kind of, I mean, you already done it in the first assignment, right? It's a flip-flop. So, this will be a clocked comparator. So, meaning this will have a clock and you slice it at the edges of the clock. That is once every cycle. Okay. So, typically you use a regenerative comparator because regenerative comparator gives you much more gain. Okay. You can see that quite easily. But let's say this is a regenerative comparator and you can potentially use your flip-flop to implement this function. Okay. So, you evaluated the sensitivity of your flip-flop to be what, some 25 millivolts or something. So, that means that if it's more than 25 millivolts, it's able to resolve it into digital outputs. Okay. So, this is what is the decision block. How do we measure the error? I mean, so these are, see, all these circuits, there are lots of degrees of freedom. Okay. When I say you implement a flip-flop, perhaps you say that, oh, I'll implement it in some other way. That is perfectly fine. This is one way of doing it. Okay. So, typically it will be some kind of latch state because that gives you a large gain. Okay. So, this will give you, essentially you have the input Y here and you get Y hat at the clock edges. How do I get the error E? Okay. So, what do you want to do? You want to do something like this. So, he says now this is a differential pair and the output current is, when it's in the linear range, proportional to the difference. Okay. And you can of course convert the output current to a voltage in various ways. Let's say we put resistors here. Will this work? What are the potential problems with this? Huh? No, but what is the problem with it? It's not linear. Okay, let's say I make it linear enough. Yeah. Okay. So, fine. So, one objection was that it is not linear. It is linear only for small differences. Firstly, yeah, that's true, and I can also control the linearity of this by adjusting the gate overdrive of the differential pair transistors. Right? If I increase the current density, it will mean a larger overdrive, so greater linearity. But also it may not be a serious objection because if we decide to use sine LMS, we need the sign of the error. We don't care about linearity so much. What else is the problem? So yeah, first thing, so Y and Y, so you say that it will be fully differential. Is that the problem? Yeah, okay. Firstly, this current source will not be ideal, the tail current source. So there will be some common mode gain also. So it will not work as a pure difference amplifier. If Y and Y hat are both large, it will give you a different thing than if Y and Y hat are both small. But if we, that is true. That is true to some extent. But if we look at the output difference, then that is not so sensitive to that. Okay. So the other, what were you saying? Yeah, actually that is an important thing. Y hat is delayed with respect to y. Is that of concern or no? It can be, if you remember the graphs, the fraction of the delay, the delay as a fraction of the symbol period was significant. It was definitely not negligible. Okay. So you are relying on, and this y hat, it is a digital signal, but it does not look like this, right? You remember how ugly it looks. It can look, especially if the amplitude of y is small, it can look like this. Okay. So it will amplify the difference and then it will regenerate, and it may barely reach the value that represents the digital logic values, okay, logic levels. So that is a problem. So when you, y hat represents a digital signal, but it's not a waveform that has only two constant values. It is a waveform which goes through all kinds of values, and also it is delayed with respect to the input. By the time, when will it get regenerated? Okay, let's take it one at a time. First thing is, yeah, fine, the output has continuous variations, but why do I care? Is that a valid thing? He says that the output of the comparator, it takes some time to rise, so it amplifies in half a clock cycle and then it regenerates in the other half clock cycle. Okay, maybe I will draw it neater. So let's say the clock is like this, it is periodic, and the flip-flop samples in this space and holds in this space, samples here, holds here, and so on. Okay. And typically, if you have, let's say in the sampling phase, the input y is relatively small. That is possible, right? It's the analog signal, the output of an equalizer, so it can have a small value. So the input is small and positive. This is y, and then it maybe changes to small and negative and so on. Okay. So the output will look like, in the sampling phase it will amplify to some extent, and in the hold phase it will regenerate it to logical values, and in the next time hopefully it will amplify to a small negative extent, and it will regenerate it and so on. So at the end of the hold phase it has regenerated it. Okay. So what were you saying? No? Okay. Yeah, now he says you compute the error at the end of the hold phase. You ignore all these values anyway. You look at the error only at this instant. Is that okay? We have the clock already, right? By the time y also would have changed. See, actually this, so in this equation, so I have written it like this, the time dependence is not very clear, but you have to multiply E at a particular instant with the gradient at that instant. Okay, so if you have relative delays between the two, it won't work. The algorithm won't work. The algorithm works only when I assume that y is a linear combination of certain inputs. So that linear combination holds for all time, right? So the inputs at a certain time give you y at that time, the inputs at the next instant give you the y at the next instant, and so on. Okay. So when computing the error, let's say you compute it at some particular absolute time t, then all of the gradients should be evaluated at the same time t. Okay. So if you have delay through this, it won't work. That is one thing. And secondly, you are not even getting the right value, right? Y minus y hat. What is that? The y hat, this value of y hat is a representation of this y. Okay? But at the end of clock cycle, you will get y hat minus some other y, because y itself is changing. Y itself is continuously changing. Yeah, firstly, it can come out of a sample and hold, or it may not. Okay? That you can't control. Right? And even if you have a sample and hold, it can change a little bit. It's not as though it will hold it exactly constant. Okay? You can sample in the middle of the hold phase. No, even then there will be some delay, right? Because what ideally the flip-flop is evaluating What is this value? This is the sign of the input at the falling edge of the clock. Okay. But at the falling edge of the clock, you don't have access to y hat, so you can't really do this. The delay problem is just too much. You can't get around that thing. Okay. So what else can you do? Delay the input. Which input? How will you delay it? No, but how do you know what the exact delay is? No, it can't be too large either, right? Or I am not understanding your suggestion. So how do you propose to delay this? Yeah. Yeah, that's true. That sounds like a. Well, let's see if that works. So let's say we have a sample and hold, and the clock for the sample and hold is the same. Okay, that is when this flip flop goes into hold mode, the sample and hold also goes into hold mode. Then you can say that the value ys you get here corresponds to the sign of y. Okay, but you need a sample and hold which can sample analog values. So let's focus on sign LMS. Is there some? So this is fine. Now you have to subtract ys and y. Okay, and this difference may be small or large. Okay, in fact, if the equalization is working properly, this y will be very close to plus or minus 1, which is y hat. So the difference will be small, and you have to take the sign of that. So this in principle works. There is no problem with it, except you have to somehow make sure that the sample and hold and the flip flop work in more or less the same way. That is, if you apply identical clocks, they do sample at identical instants. Okay. So this is something like this, but is there a simpler way of getting this? I mean, what are the other ways of getting it? I mean, this is like an open-ended question. You can come up with all kinds of things. Huh? Yeah, but it's not usually a desirable thing because you want to clock it. Like I said, if you use a unclocked comparator without regeneration, it gives you lower gain than if you use regeneration. Sign of y hat is y hat, right? Yeah. I mean, y hat is greater than y. No, I didn't say that. No, I didn't understand this. What is this? What did you say? Y hat is? Yeah. Not necessarily. It could be, y could be large also, right? This is an equalizer with coefficients which are not completely decided. So it could be large also. So it's not true that y is always less than y hat. It could be greater than y hat. And in fact, if you recall your I diagram, so it looks something like this, right? There is a spread in values. So this is what corresponds to plus 1. So you will have values greater than and less than plus 1. I mean, if you have a channel with some impulse response and you have a certain cursor value, the resulting values in the I diagram will be more than the cursor and also less than the cursor. No, you are confusing things. See, y hat will regenerate to a positive value if y is greater than 0, not if y is greater than y hat. Y can be greater than 0, it can be small or large. Of course, it can't be arbitrarily small because of the limitations on the flip-flop. So in your particular case, in your first assignment, you saw that if y is greater than 25 millivolts, it's able to detect the sign reliably, right? Yeah. Well, I mean, 1 meaning in a symbolic way it is 1. In reality, it will be so many millivolts, right? You decide what it is. You interpret it as logic 1. Yeah. So what else can you do? What is the quantity we want? In the sign algorithm, we want sine of y minus y hat. Okay. So what are the possible values of y hat? Plus 1 or minus 1. So you need either sine of y minus 1 or sine of y plus 1. So how do I get, so this 1 again, it is logic 1. In terms of voltages, you have a certain voltage that corresponds to logic 1, maybe 200 millivolts or something like that. Okay. Whatever value it is, you decide for your system. So how do I get y minus 1? How do I get y minus 1 from y? There are various ways of doing it. It's an amplifier with an offset, that's all, right? So you could do something like this, y and 1. Again, this 1 is logic 1, okay? Whatever voltage corresponds to that. So the output will represent y minus 1, and if you have y and minus 1, where again this is logic minus 1, the output will represent y plus 1. And how do I get the sign of this? No, but what is the, it may not be large enough, okay? So how do I get the sign of this thing? At a particular instant, also there is no sampling here yet. So I want to get the sign at a particular instant. How do I do that? How did you get sign of y? How did you get this? Using a flip-flop, right? So we can do the same thing. So generally what you do is you take y and you can subtract plus 1, you can subtract minus 1. Again, plus 1 and minus 1 are the logic levels. So you have to subtract the appropriate voltage which corresponds to these logic levels. Okay. And you pass it through flip-flops. Okay. This is the clock. Is this okay? So now you get sine of y minus 1 here, sine of y plus 1 here, and one of these is the correct one that you want, okay? And those two. No, that's not correct. No, not necessarily. First of all, sine of y minus 1 will never be close to 0. So you simply select it, right? You select it based on the value of y. If y is 1, you should take this. If y is minus 1, you should take this. Okay, so you put it to a mux, which is selected based on the sine of y. Okay. So this is typically the practical implementation of sine of y minus 1 or y plus 1. The advantage of this is you are simply subtracting a DC value. This is not much of an overhead. This is much faster than trying to take the difference between comparator input and output, and there is no delay involved here. Okay. And if there is a delay in the addition, so okay, firstly let me say that there is no delay involved, at least not the kind that we saw before. You are not trying to find out the difference between a comparator input and comparator output. One of them is continuous time, the other one is sample data, and it represents a logic level, but it is not a square wave. So when you take the difference, you will get very inaccurate values, okay, because of the delays. Whereas you don't have that problem here. You take the sine of y minus 1, y and y plus 1 with the same identical flip-flops, so they all behave identically. Okay. So what do you do if you have delay through this? You can put the delay in y also, right? So you can have the same, whatever block you use for summation, you simply add 0, that's all. Okay. And there are various ways of implementing this summation. One is with a differential amplifier, the other is with capacitors. For instance, you can charge a capacitor to a voltage that represents plus 1 and place it in series, or charge a capacitor that represents a voltage corresponding to minus 1 and place that in series. Okay. So there are various things, but let's for now stick to this more continuous time type of implementation. Is this okay? Is this clear? How we are doing this? And also why we are doing this? The reason is you can't take the difference between the flip-flop input and output because of the delay through the flip-flop. Okay. And the output is not a fully settled waveform all the time. So this is the architecture. This ensures that the delay is the same. I mean, the instant at which you slice y minus 1 or y plus 1, the instant at which you evaluate the sign of y minus 1 or y plus 1 is the same instant at which you evaluate the sign of y. Okay. Synchronization is present in this because all flip-flops are clocked with the same clock. If there is any error, that is because of random mismatch between the flip-flops. So we already have these flip-flop circuits. We have our familiar flip-flop with two differential pairs. Let's say we continue to use that. We have sampling in one phase and latching in the other phase. Okay. So this takes a differential input. So now for slicing y this works, and typically I already said that everything at high frequencies is implemented using differential circuits. So this will give you the sign of y when y is a differential signal. Okay. Now I want the sign of y minus 1 when y is a differential signal. How do I implement that? You have one more differential pair in parallel with. So how do you do that? So I have another differential pair and so you mean this one? This one or this one? This one, yeah. So it's actually quite simple. So you had one differential pair before. You can split that into two parts. Okay. So let's see. Now let's not worry so much about the flip-flop. Let's talk about taking the difference of two signals, each of which is differential. Okay. That's what we want now. So if we have two single-ended signals, we can take the difference between those two by using a differential pair. But we have now two signals which are different, each of which is differential. We have to take the difference between the two. So let's say we want to just make an amplifier. Output is A times x1 minus x2, where x1 and x2 are each differential signals. Okay. So let's follow the suggestion to make two differential pairs. Okay. So where do I apply x1 and x2? Can I do this? So x1 and x2. What will be the output? So let's say each of the transistors has a transconductance GM in the quiescent condition. What is the output V out? GMR into x1 minus x2. Is this okay? So, but this is not, okay, let's see what happens. Let's say x1 is 500 millivolts, x2 is 490 millivolts. What happens? So let's say let's first take the case where x1 is 20 millivolts, x2 is 10 millivolts. The difference is 10 millivolts and the output is supposed to be proportional to 10 millivolts, GMR times 10 millivolts. So if you put 10 millivolts here, 20 millivolts here and 10 millivolts here, each of the differential pairs works in the linear region. Okay. So these currents will be proportional to the input voltage and you subtract the currents. Now I go to this case. I have 500 millivolts and 490 millivolts. Each of the differences is large, but the difference between x1 and x2 is small. What happens then? What do you get at the output? Okay. So what do you get at the output? Huh? What will you get? No. So the tail currents will be the same because otherwise, first of all, I could not have identical GMs, right? So the tail currents of the two are the same. I0 and I0. So what is this output V0 when x1 is 500 millivolts and x2 is 490 millivolts? And it is 0, right? This differential pair has all its current steered into this transistor. This one has all its steered into this transistor. So the output voltage is 0. but that's not what you want. You should have got the same result as here. So how can you fix this? In fact, see, the difference is still small, x1 minus x2, but each one is large. You should be able to handle this condition, and this can easily happen because you see that, like I said, in the I diagram, let's say this is the midpoint here represents logic plus 1. Okay, so you in fact almost always have values which are around this plus 1 value. Okay, that you have to compare. At the sampling instant, if the sampling is in the middle of the I, you will have values around plus minus 1. So the value itself is large, but the difference between the inputs is small. So should I modify the circuit or what? Huh? So if I connect it like this, there is a problem with saturation. As the input increases, it will have a problem. Okay, it will have a problem. I mean, even if it's not saturated, you will have a problem with linearity. You will not get something that is proportional to x1 minus x2. Okay, because let's say it's some intermediate value now. x1 is 150 millivolts and x2 is 140 millivolts. Now each differential pair is not fully saturated, but they are operating at different points of the nonlinearity. Okay, so the gain through this differential pair is different from the gain through this differential pair. You understand that, right? So the characteristic of the differential pair looks like this. So if one is operating here and the other is operating here, the slope is different. So you will not get something that is x1 minus x2. You will get some function of x1 minus some function of x2. Okay. So the solution to this is not to apply the signals the way I did, but each differential pair gets a signal that comes from both x1 and x2. Okay. And what do I apply here at this point? x2 minus is what goes here. So this will be x1n, x2n, I think. This will give you the right value. Okay. See, when we want to detect the difference between x1 and x2, and in particular, in most cases we are interested in this value when the difference is small. Okay. When x1 is overwhelmingly large compared to x2, it's easy to take the difference. If the difference is hardest to take when the two quantities are similar. Okay, that's where the sensitivity and all of that comes into picture. So the whole circuit should work properly when x1 and x2 are close to each other. Okay. Yeah, actually, so that is the problem with this. So first let me complete my description. First let's imagine that x1 and x2 have the same common mode voltage. Okay. So x1p is x common mode plus x1 by 2. And x2p is x common mode plus x2 by 2. Okay. So the incremental current in the first differential pair is proportional to this quantity. Okay. And the incremental current in the second one is proportional to, this is minus x2 by 2 and minus x1 by 2. This is what you should get. Okay. So the common mode terms will cancel out and you are left with the differential terms. Now this will take the difference between x1 and x2 even if each of x1 and x2 is a large value. Is it okay or no? Now the problem is what happens when the common mode voltages are different. What happens if the common mode voltages are slightly different? Common mode voltage will get amplified. Let's say the difference is, there is a difference but not very large. Let's say there is a 20 millivolt difference. And there is a difference of 20 millivolts between the common mode of x1 and common mode of x2. Okay. It will get cancelled. So actually that's what happens. Anyway, you think about it, we can continue it afterwards. But for small differences in common mode voltage, it does work properly. Okay, it's only when if the common mode difference is very large that it fails to work, but if the common mode difference is small, then it does work properly. For instance, let's for illustration take x1 and x2 both to be 0. Okay, so this is a clearly silly case, but let's not have this. Okay, so I have xcm1 minus xcm2 in one of the. So firstly, I should have said this is this times gm and this times gm if the differential pairs are operating in the small signal region. Okay, if the common mode signal difference is small, they will be operating in small signal region, and this will cancel out. This will give to you 0. The contribution of the common mode difference is 0. The common mode difference is very large. I can't write this times gm and times gm. It will be something different. So in that case, it won't cancel out. But if the common mode voltages are more or less equal, it works. Okay, and it works for large values of x1 and x2 also. This is okay. This is known as a differential difference amplifier. So basically, it's a differential it's a difference amplifier, each of whose inputs is differential. Okay, and this is also used in many other analog circuits as well. And one of the things which you can use it for is something like this, where you need to take the difference of two differential signals. Okay. Any questions? No? Okay.